So this is a problem that's sending a spacecraft to the moon. And the way they do it is they have it in a circular orbit, very close to the Earth. So we just say its orbit is at the radius of the Earth in a circular orbit, little r0. And then right here at perigee, they fire the rockets and send it out into a big orbit to the moon. And so in the big orbit, this is still perigee, because it's still the closest it gets to the Earth, and we don't worry about the fact that it's orbiting the moon out here, or it gets to the moon, or whatever it does out here. It's really just going to the moon there, so I should probably have this maybe over here, something like that. But it's on an orbital path that looks like that, and so r0, this piece here, that's r0, is just essentially the radius of the Earth. We're saying it's in a very low Earth orbit, and this is r1 here. So this is perigee and apogee for both the circular orbit, I guess. The r0 is the perigee for the circular orbit, because they're all at r0, the whole orbit is at r0. And then it's perigee for the big orbit, and then apogee for the big orbit is r1. And so what we want to know is, what's the percentage increase in speed here to get to the moon if it starts in a circular orbit and the boost is at perigee? And so I wrote a bunch of this stuff down, but let me just see if I can just sort of back it up a little bit and say, so the perigee distance is just a minus epsilon a for the circular orbit, which is just alpha over, hang on a second, it's alpha over 1 plus epsilon, because the lattice rectum is a times 1 minus epsilon squared. And so, but for the circular orbit, that piece is just 0, so it's just alpha, and alpha is just ml squared over k. I put LC for L for the circular orbit because that's going to matter. And then since the circular orbit is at its closest approach, and there's no angle, the angle is 90 degrees between the radius and the velocity, then that's just equal to m r0 squared vc over k, and all that is from r0 here, and so what we get is r0 is equal to k over m vc squared, or as we'll use later, k in this case is equal to m r0 vc squared, where again vc is the speed it has in the circular orbit, and we're going to use, I think, v0 for the speed in the elliptical orbit. And so so now we kind of step on the gas, and we've now changed the problem a little bit. Here again, r0 is equal to alpha over 1 plus epsilon, but no longer is this 0, right? This is now I have a highly eccentric orbit, which I can sort of figure out here if I want to. And so this becomes I've lost it for a second. I'm going to solve this for epsilon, so I'm going to get epsilon plus 1 is equal to alpha over r0, or epsilon for the eccentricity of my orbit is alpha over r0 minus 1. And so I've just rearranged this. So this is once we've stepped on the gas, and again, no longer is my eccentricity 0 like it was here. It's non-zero, and I'm going to solve for the eccentricity for this orbit. And so I'm going to start on the next screen with this equation. And so this is what I had. I had the eccentricity is alpha over r0 minus 1, and this is just ml squared over k divided by r0 minus 1. Right? This is the angular momentum per unit mass with where the thing's been boosted, right? And so this is equal to m. I'm going to call it v0 r0 over k r0, except this is squared and squared. So this is m L squared, which that's what the v squared r squared is, over the k times r0 minus 1. That's what the eccentricity is. Or the eccentricity is m v0 squared r over k minus 1. And so the eccentricity then, if I grab the k from earlier where I wrote k in terms of the circular orbit, it was equal to m vc squared r0. That was an r0. And so this becomes m v0 squared. This is my boosted speed, r0, over m v circular squared, r0, minus 1. And that's my eccentricity. And so the m's go and the r0s go, and this gives me my boost speed. It says the ratio of v circular orbit, the v elliptical orbit to v circular orbit squared is equal to 1 plus epsilon. And so we've got to figure out how to get this from the information we know. And you can get the eccentricity from the two radii, right? R1, so if this is my orbit, here's where the sun is, right? This is R1, and this is R0, right? And so R1 is equal to A plus epsilon A, and R0 is equal to A minus epsilon A. And so you have to figure out how to tease the eccentricity out of that. If I subtract these two equations, I get R1 minus R0 is equal to 2 epsilon A. If I add those two equations, I get R1 plus R0 is equal to 2A. And so I get epsilon is equal to R1 minus R0 over R1 plus R0. And so I'm going to stick this in, since we know these numbers, I'm going to stick this in for here. And so I'm going to say, I'll just write it over here, v0 squared over v1 squared is equal to r1 minus r0 over r1 plus r0 plus 1. This you can evaluate, right? This is 60 RE minus RE over 60 RE plus RE. The RE's cancel, and you get 60 minus 1 over 60 plus 1 plus 1. And so you get V0 over VC is approximately the square root of 2. It's about 1.4. And so that's what the boost has to be. Did I get all that in there? It might be a little better.